Back when we very first started looking at linear equations and expressions, we were modeling them by stacking a stack of styrofoam cups. And you might remember that really a stack of styrofoam cups is the height of one cup's body plus a bunch of rims. And the rims would be the total number of cups. So we wrote an expression way back then, recognizing that the height of the body of a cup would be 7.8 centimeters when you do 9.1 centimeters minus 1.3 for the rim. And then we basically were just adding a whole bunch of rims. So 1.3 multiplied by the total number of rims, if we're letting x represent the number of rims. And that essentially gave us an equation. In this case, it represented the height. So based on the work we've been doing recently, this should make a lot of sense to you. That when we are looking at stacking cups, we're repeatedly adding, and therefore it's a linear equation. And so if we are asking the question of like, hey, how tall would it be, or how many cups would it take to be 100 centimeters tall, we could certainly replace y with 100 and 100 centimeters, and then basically go about solving it by using inverse operations. And that's all fine and good. Algebraic solving is a great strategy, but it's not the only strategy that we should have in our tool belt. And so what we're going to do next is try to take a look at how we can solve equations without doing all the algebraic symbol manipulation. One of the tools that we should now have in our arsenal or in our tool chest is the idea that we can represent these relationships graphically. And to understand what a graph really is, most students don't really understand. They don't really get it, even though it's a very simple idea. They generally think that the goal is simply to create a line or something like that. But really, graphs are all about reading information from them because what they show is possible inputs and outputs. And so they're very powerful tools. And we're going to be using Desmos today. I'd encourage you to go ahead and pull that up on your phone or on your laptop and punch in this exact same equation that you see up here that we just wrote. So if you look on here and you click on the points, you'll recognize that as you drag along, you can get values, and Desmos does a great job of giving us this. So for example, this point 2439 really means that we have 24 coffee cups and the height of the stack is 39 centimeters. So we could scroll along if we were interested in how many cups does it take to be 100 centimeters. We could probably scroll along here and eventually get pretty close, although it looks like we can't get exactly there, which is troublesome. So we can recognize it's right about 70, 71, somewhere in there. But that doesn't give us an exact answer, it's only approximate. If I wanted to get a more exact answer, I need to recognize that first this equation is equal to y. That is, y represents the height. Okay? So if I put in a number of cups, obviously the value of y is going to change. It's going to depend on what value of x, number of cups, that we used. So let's go ahead and just try a new equation in here. And this equation I'm going to write for the height. So I'll just say height equals 100 centimeters. And you'll notice that gives me a line that it basically is kind of like one that you've seen before. Should have seen it in Algebra 1. But it's essentially showing you every single point on an entire graph that has a height of 100. Desmos recognizes that this is a point of interest where these two graphs cross each other or intersect. And so if I click on this point right here, it's going to recognize the intersection, which means that intersection is the one point on the graph of the cups whose input, 70.923, results in an output of 100. If I was going to go back and solve my equation that I was doing earlier, if I solve this, I'm going to get that exact same answer. In other words, the graph can give me the same answer that the algebra gives me. And that's what we're really focusing on in this particular idea. Let's take a look at a second example. So certainly, again, like the previous problem, we could solve this equation by using inverse operations and getting rid of fractions and all that same kind of stuff that we've been doing. But now we're really trying to take a look at these equations from a totally different perspective. You'll remember that when we solve an equation, we talked about this early on, especially with the idea of a function machine, is that when you have an answer like x equals, what you're really finding is the input that results in an output of 14. And that's really all we're after. So a graph, and especially using technology to help us graph, is a very, very helpful solution to finding an answer to this question. While we could do the algebraic symbolism, we want to be able to be flexible. So what does this mean? How would I solve this by graphing? So I've gone ahead and in Desmos plotted these two functions. Basically, I've plotted the left-hand side, which is looking for the outputs of this expression. based on what the x value input is. So for example, if I put in 0, we expect that we would get a 12, right? We've been doing work with intercepts and slopes and stuff like that. And that point makes a lot of sense, right? Put in 0, get out 12. It's like your initial amount, and then you have a rate losing 1 as you gain 3, right? So every single point everywhere along here, including these decimal versions, are the results of putting in the x-coordinate, the first number, that's your input, and getting the output. So the graph visually shows you what that's all about. So the point we're interested in is when our output of this is 14. That's why I'm writing a second equation. So as I write that second equation, this equation is going to plot, and it's going to show me every single possible point on the graph that has a y value of 14. You'll notice the x doesn't matter at all. So the point where they intersect is one of importance. It basically means that on the blue line, the only time you're going to get an output of 14 is when your input is -6. And therefore your solution to this question would be to say x equals -6. So that's not going to work very well for me. X equals -6. So all you would need to do if you were trying to communicate this to somebody is simply to create a quick sketch of this. So if I was going in here, I'd make my graph, and you notice that one of the lines was at y equals 14, and the other one was going something like this, right? And the point where they intersected right there was -614. And therefore I would just say, hey, my input value is -6. That's the answer to this question. That's the input number that gives me an output of 14. So that's what you should do. Here's what you should not do. It is an utter fail if you do this. Just simply come into Desmos and graph 12 minus 1/3 x equals 14. Sometimes Desmos will be kind and solve it for you, but this is not anything where I can put in an input and achieve an output. Okay, you'll notice that it does give you a line at where all the coordinates on the line are -6, but that's really not what I'm all about. What I really need is to graph the left-hand side as a y value or an output, and the right-hand side as a y value or an output, and I just need to find out when are those outputs going to be the same value. So please don't do this. That is a bad, bad move. So what if we were asked to solve something like this by graphing, which looks really scary? So first of all, what you need to recognize, again, we can solve this by algebra, but you'll notice that on the left-hand side, this is never going to give you a single number output like we saw in the previous example. Whatever value I choose for x, I'm always going to be getting a different value for 10 minus 3x, right? So that depends on the value of x that I choose. And likewise on the right-hand side, this is never a single constant number. It's always changing based on the value for x that I use. So when we were algebraically solving this and we did all of our symbol pushing around and multiplying and all that kind of stuff, we got an answer again of x equals. And again, what that was really trying to ask us was, what is the input value? So that when you put that input number in here and you put that input number in here, you get the exact same output. In other words, the left-hand side and the right-hand side come out to be the same output. So how would we solve that? By graphing. Well, do the same thing we did before. Take your left-hand side equation and plot it in Desmos. So you can see that 10 minus 3x is our left-hand side. And again, what that means, you'll notice I'm saying the same thing over and over because I'm trying to make sure it makes sense, clicks in your head. It's a really simple idea, but really hard to wrap your mind around, is that this is showing that whatever the number I put in, that's the first number, I'm getting a different output. So as I scroll along here, I'm getting different outputs all the time. And likewise, on the blue side, the right-hand side, I'm putting in different values for x, and I'm getting out different values for y. But the question says, when is their y value, this number, and this number, going to be the same? What number do I put in for x so that I get the same number for both? And the answer is the intersection point. So in this case, since I have an intersection at 3, 1, my answer is the input x is 3, and the output is 1. That would be y. Now, you don't see a y in the problem, right? There's no y here, but you have to infer that because we've been doing so much work with input and output. And that's really what it means to solve an equation. I don't know if you ever realized that before. So what you would do to show this answer is simply take a picture of your graph and just do a quick sketch. So we have one that's going like this, one that's going like this, and the point at which they intersect is 1, 3. Did I have that right? Was it 1, 3 or was it 3, 1? All right, perfect. It was 3, 1, so I've got it backwards. So take that off, put in 3, 1, and therefore from this, the answer that I'm interested in is x equals 3. If I put in 3 to each side of the equation, so the left-hand expression and the right-hand expression, I get 1 out of each one. And you could verify that, but I'm not going to take the time here to do that. So that's really it. That's what it means to solve equations by graphing. And the powerful thing is that it allows you to solve equations that you have no idea how to solve algebraically, or may even struggle algebraically. So it's actually a great way for you to check your answers, and that's something that we'll be doing as we come up.